2024, 600 megawatts of solar PV panels were installed across the world. Solar energy has come a long way. Since the early 2000s, we have installed close to 2,000 gigawatts. But this revolution in solar energy couldn't be possible without one simple ingredient. Sand is the source of all silicon extracted on Earth, and silicon powers almost all solar cells in today's growing market. To generate solar energy, we need two types of silicon semiconductors, a P-type and an N-type. Each layer has its own molecular structure essential to the flow of current through the cell. But to achieve these electrical properties, we use a method called doping. Silicon doping is just one of the 4 steps we will cover today as we discover how we transform the second most common element on Earth into a versatile semiconductor. This is the science behind silicon. Solar energy has come to dominate the global renewable energy market. Within the last 20 years, the world has experienced a massive increase in solar energy installations. With cost per unit of energy dropping steadily, PV has become not just a sustainable but also economical solution. This could be attributed to the mass production and economies of scale that PVs are experiencing. The backbone of this growth is silicon. Silicon could be found in virtually all microelectronics, computer chips, and PV panels. It is the 7th most abundant element in the universe and the 2nd most abundant element here on Earth. When extracted from Earth, silicon isn't pure. It's coupled with a pair of oxygen molecules, silicon oxide, also known as silica or quartz. Now, silicon is a special type of element. It's neither a metal nor a non-metal. It's somewhere in between. The correct term is metalloid. Silicon is a semiconductor, meaning it does not naturally conduct electricity. However, its conductivity gets better as temperature rises. It's extensively used to make transistors, which I'll be covering in another video very soon. After we purify it, the end product looks something like this: a silicon wafer. To achieve this level of precision and purity, we pass silicon dioxide through 4 stages, the first being a furnace. Upon reaching its melting temperature of approximately 2200 degrees Celsius, most impurities are removed, and what's left is a 98% pure silicon ingot. Solar cells require highly purified silicon, almost 99.98% purity, which is where the purification stage comes in. The concept is pretty simple. Silicon ingots are subjected to a floating zone process. In a nutshell, the ingot is passed through a heated zone for a number of times in the same direction, which allows impurities to move to one end of the ingot. By the end of the cycles, all impurities are concentrated in one end, which is then cut off, leaving behind the pure silicon. This thermal process is also important as it manipulates the crystalline structure of silicon. The third stage, doping, is the basis of a solar cell's operation. You see, silicon is doped by thermal diffusion. The process involves heating silicon in a closed vessel and exposing it to phosphorus or boron gases. Their molecules diffuse into the silicon as temperature rises. The higher the temperature, the deeper the diffusion, meaning that temperature is the way in which we control the diffusion rate of these gases. These elements are essential in creating P and N-type semiconductors. To keep things simple for this video, keep in mind that P-type semiconductors have extra empty spaces or holes, while N-type semiconductors have extra electrons. These changes in the molecular structure of silicon are the basis of how a solar cell generates an electric current. When doping is complete, silicon is cut off into thin wafers and shaped. For solar panels, generally being rectangular or hexagonal. Quite recently, research has shown that a rougher surface finish increases the absorption of sunlight, leading some manufacturers to skip polishing the surface of wafers entirely. But not only that, actually making it rougher to enhance the efficiency of a solar cell. A solar cell consists of a P-type and N-type silicon wafer and a PN junction. But there are other layers which are essential to a commercial solar panel. As silicon is very reflective, an anti-reflective layer is added on top of the solar cell to reduce the sunlight reflected back into the atmosphere. This increases the absorbed sunlight by up to 35%. This coating is also a safety precaution when PVs are installed near airports, as their glare could affect pilots' visibility. Guys, as you may notice, we aim to create the best educational content in a concise and simple way. We're currently working on building a website where you can subscribe to our 3-minute fun fact newsletter. So, as always, we appreciate your support. Stay tuned for next week's video as we dive into the science of generating electricity from PV and connecting it to the grid. But for now, watch this video if you want to learn more about wind energy.